form on. Yeah. You wait 5 minutes and yeah.
ಅಂದ್ರೆ ಕೆಮಿಸ್ಟ್ರಿ ಅದ
Okay, you are coming. No. Yeah, please. No. I would just ask you that do you want to speak something in the beginning?
Yeah. Morning, everybody. So I can see the smile, the face, on the face of all the participants. Because today is the last day of the GIAN program. So I hope, you will be returning home today. And sorry for all the trouble we have given. Yeah. And today we have two important lectures from Roy. Corrections in the activity determination. This is very important. And those who are in take up gamma spectrometry and alpha spectrometry as one of your research areas. So this will be highly beneficial. So I request Roy to deliver those two lectures, and we have a exam immediately after that, and then we'll have the formal closing ceremony. Then we'll have lunch and say bye-bye. Yes.
Nice plan. So, good morning again. I hope that you are prepared for the examination. I quickly looked through the questions and they were extremely difficult. I wouldn't pass that. Sorry, don't believe me. I will put here. All right. So in
the questions from your presentations.
sorry.
Can you give clue? What are the questions? Can you give clue?
I have a microphone here. Okay, questions are not complicated. All right. Here I talk about corrections mainly from the point of view of gamma ray spectrometry, but of course these corrections can be used for alpha spectrometry too. So these are the main corrections: radioactive decay, self-attenuation or self-absorption, and coincidency correction. So, simplified equations that I showed you in previous lectures, they didn't take into account corrections. So, more precise equation is following and these corrections may be applied to this here and here. So as I told you, these are the main corrections. So radioactive decay correction goes mainly to that point, and also self-absorption, and also coincidence correction too. These corrections can be taken into account in different ways, depending on how the activities or activity concentrations are determined in practice. So these correction factors can be computed separately, multiplied together, and applied as shown in the above mentioned equations. Some of the corrections, like the self-attenuation and geometry corrections, they can be or are computed by an efficiency transfer program such as FTRAN, which can be as a part of the analysis process. So you do not need to do corrections by hand. So the software can do this. So in Stuk we analyze typically 2,000 to 3,000 samples per year, and their characteristics are different. Different measurement geometries, different compositions, etc. So we are using FTRAN in routine basis. Let's look at the correction for radioactive decay. You know certainly this picture. This is timing, and this is number of nuclides in some sample. Starting point is 1 million nuclides in the or activity in the beginning of time. After one half-life, there is only 500,000%. Secondly, there are 250, etc., etc. But when you determine the activity, you have to select what is the correct time when you report your results. Is it here, here, or where? That's one of the key issues. So number of radioactive nuclide reduces as a function of time. You know these equations. You must specify the time to which you report the activities. Here is an example for air monitoring in case of continuous sampling versus separate sampling and counting. In case of nuclear power plants, they often use continuous air monitoring. And if we assume that the concentration of radionuclides in air, inside air or outside air, is constant, and if we use continuous air monitor and we start sampling here, it activity in the filter behaves like this. After some time, there is a balance because of radionuclide decay. This happens in the case of separate sampling, and after sampling, we take counting. So here we take a sample, for example, 1-day sample. It takes some time to change the filter, and here we start counting by using alpha or gamma ray spectrometry. So, for example, in the case of CTBT organization, this time here, it's, if I remember this correctly, it is 1 day. Why do you think why they do things like this? So there is 1 day decay, and question is air sampling and then detecting possible gamma ray emitters in the sample. Why 1 day? All right, I will explain. The reason is that sorry. There is radion daughters in the air, short-lived ones. You remember lead 214, bismuth 214. So they want better background, as low as possible, and within 1 day, these nuclides, short-lived nuclides, has decayed off. So, when counting starts, and ends here, the DC, you can see the text here, or you cannot see the text, but it's basically you can see the text later. But typical reference time is in the middle of counting time, or in the middle of sampling time. Depends on the cases. So, because of this behavior, we have to correct decay. So counting correction C1, which is this one, it compensates the decay during counting, where T is the counting time here, and T is the half-life of the nuclide in question. And counting during the waiting period, C2, compensates for the decay before counting. Here. This TW, it's the waiting time. So if you want to calculate these corrections by hand, it's of course possible by using, for example, this program. There are a lot of applications in it. This is one example. So you perhaps know these Bateman equations. It's a full descriptions how radionuclides, I mean the series of radionuclides, are behaving as a function of time. But commercial spectrum analysis software usually incorporate almost all these corrections. Let's look at the correction for self-attenuation. So in terms of metrology, the gamma ray spectrometry is a secondary method, which means that calculating the activity of the sample of interest, the result is compared to that of the calibration, so calibration standard. And the point is that usually the sample characteristics are different compared to those of the standard, at least in our cases. So in Stuk we are measuring so many different type of samples. It means that attenuation of gamma rays in the sample itself is different. So as you can see here, we can call gamma behavior like this. It's a self-absorption. In this case, we can call self-attenuation, which are more or less same thing here. However, energy of this gamma is different than the original gamma. So this doesn't go to the full energy peak. So different attenuation may be due to different sample size, I mean diameter and sample height, different sample density, and of course different elemental composition of the sample. There are two main concepts that deal with this area. Linear attenuation coefficient. It quantifies attenuation per unit length, for example, per centimeters or millimeters or whatever is the unit. However, mass attenuation coefficient is more useful because there is independence of the material density. So here is mass attenuation coefficient here, and this is energy. There are different materials here. For example, soft tissue is here, bone is here, and heavy materials here. For example, this black thick one is lead. Any ideas why in these fat soft tissue or bone cases there are no these edges? Any ideas? The binding energies of electrons in the electron cells. So the energies are low that they are not visible here. So as I have explained several times, knowing the elemental composition is important, especially for quite low gamma energies. Oh, this is interesting case that I think that I showed this or discussed this yesterday or day before that. Some years ago, I got a sample from a mining company. They gave me a beaker full of gold. The value was very, very big. In fact, they wanted to know what kind of radioactive materials, natural radionuclides, of course, are in these samples. So, previously, when I went into my lab almost 10 years ago, our efficiency calibration didn't take into account elemental composition in small energies. It took into account sample thickness, for example, and sample density, but not elemental composition. Then I used this, our old system, and the result for the peak efficiency was this as a function of time. But now, the composition is totally different compared to our normal samples, because usually we don't analyze so dense samples. I used FTran software, and this was the result. So if I have used our normal way to analyze this spectrum, I would get totally incorrect result at small energies. And in this case, small is below 700 kilo electron volts. Now you can clearly see the effect of elemental composition. Right, let's look at briefly coincidence correction things. I explained this once more, but let's do it again because this is not an easy thing. So, this is cobalt 60 decay scheme. It goes to the nickel 60. And you can see here the decay times of these levels. So it's of the order of picoseconds half-life. However, typical time resolution of electronics, it is order of microseconds. So it may happen that both of these pulses come to the detector at the same time. So what happens is that detector doesn't see that one, it doesn't see that one, it sees this one. 7, 3 plus 1, 3, 3, 2 is this. Okay, it might happen like this also. That, for example, let's go here. For example, this energy was totally absorbed in the detector, but the second one goes like this. So this is the reason of these. Because there should be, if there is no background, there should be no higher energies than this one. Coincidence correction is small when there is large source to detector distance, because if the distance between the detector and the sample is large, it's quite improbable that photons go to the detector at the same time. Coincidence correction is notable for well type of detectors. In well type of the detectors, there is a hole in the detector into which you can put the sample if you want. In some cases, gamma X-ray coincidences must be accounted for, especially in case of electron capture. I hope that your analysis software, Jenny, is able to calculate coincidence corrections. I think it can, but there are several other computer programs, such as this Eftron software, Etna, for example. They can calculate coincidence corrections. Correction can be calculated by the aid of total efficiency, but usually they are computed by using a specific software. In case of a point source, this is the total efficiency. Oh, I said previously that I send the www pages, the name of the www page to Karuna Karapati. It is shown here, so you can download it free of charge if you want.
Downloaded it available in some of the computers.
Yeah.
Some of you want to go and work, you can do that.
Yeah. It's a learning process. I mean, learning how efficiency behaves in different cases. So this is an example if we don't take into account coincidence correction. So this is energy here, and this is peak efficiency here. The maximum value is, of course, 1. This was our old efficiency curve as a function of energy. Nowadays, it is more or less same. There are no big changes. However, when I did this efficiency calculation, these are the nuclides shown as red arrow, which do not have notable coincidence corrections. For example, lead-210, and also cesium-137. They stay quite well to the curve. However, there are some nuclides, like cobalt-60, these two peaks here, they do not fit the curve. But if I take into account coincidence correction, then they are located here. So this is not fitting of these measured efficiency points. This is our old curve, which is quite good also. You can see also here the uncertainties of each point. Okay, I don't go any further for the corrections. There are some minor things that can be taken into account or not. This example I already showed you. It was yesterday or day before. And please, if you like, study EFTRAN. For example, this kind of case. Filling height, in our standard case, 2 centimeters. And if the sample contains, for example, 1 millimeter water, we can see the difference between the efficiencies. So this was my last slide, and the presentation was quite short because originally when I saw the brochure, the timing was a little bit different than the timing in the present program. I have one more presentation still, but do you have any questions about these corrections or comments? If not, I suggest then we could have a small break. Is it? Let's see.
You will appreciate these concepts once you start working in the field, because these are very important. This efficiency correction, because you can't have a reference material in all types of geometries. So efficiency transfer process or calculations are going to be essential at some point of time in your career.
Yeah.
So it is very important. You should appreciate it.
Yeah. But please note that there are several other programs that can calculate efficiency transfer or full Monte Carlo codes.
Yes.
But in the case of full Monte Carlo software, the point is that you have to very precisely know characteristics of your detectors.
Yeah, almost all the supplier will tell you whether you want basic version or the advanced version. Mark the region of interest and take the count. The advanced version will also, for example, Guinea, which we are using, has a option called geometry composer. So it does exactly same. So you can compose the you are going to use. The corrections for the efficiency for a sample which is in another geometry. So other software also have. This appears to be a very user friendly.
All right, should we have a 20 minutes break or so we can?
Yeah. Container 2. There is a point, container 2 absorber gap, the last one in the source. Go down, this one.
Yeah. Container to absorber. All right. So, in some cases, for example, in the case of CTBTO organization, they do not want to see low energy gammas for some specific reasons, which are, I think, a little bit political. But let's forget that thing. They put an extra absorber, which is shown here above the detector. This absorber prevents low energy photons to go into the detector. And this container to absorber gap, well, in this example case, this is just an example, it's a distance between the sample and the absorber, 3 millimeters.
So you mean to say there is another layer of a material between the sample and the detector?
Air.
Air.
Yeah. This is just an example. Of course, normally we put the sample just above the absorber, if any. We are not using any absorbers in Stuk.
I have one question. Aluminum detector.
Yeah.
And you have a composite entrance window, composite carbon entrance window.
Yeah.
Do you keep the sample right on the window or you keep a support over that?
No, it's practically right on the window, but this distance, I mean distance between the active part of the detector to the source itself, it is very important in terms of efficiency.
Yeah.
We have some broad energy germanium detectors, and they look like this. Sorry, I enlarge the detector a little bit, so it's like this. There is a small thin metallic ring here. This is some metal, I think it's aluminum here. And in some cases, our samples, our beakers are bigger than the detector. So size like that. All right. But the point now is that this window is very thin, 0.5 millimeters or so. I don't remember the exact number. But if you are looking it this way, the point is this. So this is the part of the metallic ring, and the window goes like this, in fact. And this is because of the vacuum inside the detector. Why there is vacuum? Do you have any idea? Because in the very bottom there is this long finger made of copper and minus 200 degrees centigrade there. So vacuum is like an insulation. If you lose the vacuum, then you have a problem. In this case, when we have a small sample, a small beaker, like this one, then the distance between the detector is located here. So there is a difference between this distance compared to this case, because bigger beaker goes there. And this distance is in fact very, very important. Believe it or not, you can use FTRAN software to test this. Because sometimes it may happen that you have a very radioactive source, very active source, and you have to put this detector sample here. And you can use FTRAN software to correct this distance. Is this the answer of?
Yeah, partially. Carbon window.
Yeah.
What could be the maximum mass? Can I place a 500 gram sample right on the window?
I think some 100 grams are okay, but I cannot exactly say the number. I know that some of my colleagues accidentally dropped some beaker there, and the window broke down.
Yes.
Then it was a very expensive repair.
So that's why, if you have observed our detector, we keep a polyethylene cap on that, just to protect the window. But place the sample right on the window. But we don't want to record. He has 18 detectors, but we have only 3.
Yeah.
So we want to take care of it.
Some detectors has aluminum housing here, and then it's
they are ready. But then with the aluminum windows, it cuts off the low energy carbon.
All right. Any other comments, please?
Yeah, if there are no comments, discussions,
For 20 minutes, then it's exactly 11 o'clock when we go back here.
Yeah. One tea now?
Yes, please.
Yeah. Deepika? ನಮ್ಮ ಲೈವ್ ಆಲ್ಮೋಸ್ಟ್ ಡಿಲೇ 30 seconds ಡಿಲೇ ಆಗಿದೆ. ఇక్కడ ಒಂದು 5 to 10 seconds ಡಿಲೇ.
All right, I think that we should start now. Somebody is missing, but let's start. You see, this course is advanced and something. Now I think that I will show you these advanced things, because most of the presentations that I showed you is more or less standard alpha or gamma spectrometry related things, but these are that I present you, these are quite new things. And I only talk about recent development in my institute. And this is important. Sorry. Do you know what's this event mode or list mode data acquisition? Have you heard this concept before? All right. Sorry. I will explain you soon. So we have several quite modern equipment in Stuk. We have alpha gamma coincidence systems, Compton suppression system, and a cosmic ray background reducing system. Let's look at the basis of the event or list mode data acquisition. What does it mean? All right, the point is here. So, single measurements, by using gamma ray spectrometry, for example, it does not necessarily give all the information needed for complete characterization of a sample. Like those nuclear bomb particles that there is another possibility. I mean, the possibility is this one. Now I assume that I am a multi-channel analyzer, and I am not now looking about the data that is coming from the measurement system. Okay, channel number 1 may contain 0 counts. Channel number 1 may contain 2 counts. Channel number 2 may contain 7 counts. Number 3, 0 counts, etc. Up to 16,000 counts, if I was correct, it was in this system, or 32,000 counts, channels. I don't remember now the exact number. Was it 32 or 16? How? 16, I guess so, yeah. All right. Now, same thing holds also for alpha spectrometers, but I think that the number of counts was here different than the 16. I don't remember, was it 1,000 or something like that? But anyway, if the number of channels are equal or not, it doesn't have an influence here. But the point is, if I put for these counts, these 2 photons that are, for example, this channel, if I put time signal, each of them, for example, this case, there is some time signal T1 and another photon signal T2 in terms of microseconds, of course, because the pulses are and clocks are very accurate. All right? Why to put time signal there? Because if you register only a spectrum, amount of data is not very big, in fact. It's, in your case here, it's 30 kilobytes around, or 100 kilobytes. But if you put signal to each photon, you make it out giga. You can apply so-called software coincidences. You can later combine these 2 methods. So it's post-processing the data instead of tedious hardware coincidences. I will explain this more. So, coincident spectra can be generated from the time-stamped data online or in post-production. So, you can see here, this is the sample. This can be gamma ray spectrometer and this can be alpha spectrometer. It emits data to both of these systems. So, access to time-dependent behavior of the measurement system that would have been invisible under normal histogram recording. This spectrum that you see on the screen or on the paper. So the point is that the detectors are running with a synchronized clock. This is important, so that coincident or anti-coincident events can be selected from the data using post-processing. So signal in both detectors within a short time window, they both come from the same event. It's possible to select between events that are anti-coincident or coincident, or fall within a specific energy window in another detector. Let's see some examples here. This is again animal name. You remember this ASI software, donkey, and bull, car. Now this is panda, developed in our institute. So this is seems to be a very complicated system, but basically there is a gamma spectrometer here and a alpha spectrometer in this vacuum chamber. All other things are not very relevant from this point of course. So particle comes, panda name comes for the words particles and non-destructive analysis. So you know that if you are using alpha method, then you have to destroy your sample by radiochemical means usually. But we don't want to do that. We don't want to destroy samples. So this equipment uses position-sensitive alpha-gamma coincidence techniques for measuring environmental samples. So there is one so-called vacuum chamber for loading the samples. It is in fact shown here. You cannot see the sample, but it goes this way into this vacuum chamber. And there is another vacuum chamber for the measurement, this one. In this case, there is no lead shielding. Why? All right, you will see it. Which is in fact not a very good thing in practice. You will see that. There is no nitrogen cooling, it's electrically cooled system, this one. This is a gamma spectrometer. Let's look at this in a realistic way. So the measurement setup consists of one high-purity germanium detector for gamma rays and so-called double-sided silicon strip detector for alpha particles. And pixel size for that detector is 3 times 3 square millimeters. So it can locate where is, for example, a hot particle in the sample. This spectrometer strip can record an alpha spectrum. The sample, for example, a nuclear bomb particle, it's shown in the next slide. It is located between the detectors. Let's forget this because this seems to be quite complicated. I will show you the principle, which is more important here. So let's begin here. Picture A. So it's a measurement setup here. So this is gamma detector here, and this is the alpha detector. And the sample is located between these two detectors. So in our example, it is a nuclear bomb particle from Thule. Do you know this Thule accident? This place is in Greenland, at very north. And I think it was 1970s or 60s when a big nuclear B-52 airplane crashed to the ice of Greenland. Fortunately, that plane was carrying nuclear bombs. Fortunately, these bombs were not exploded like nuclear explosion. Of course, they broke down, and the material went to the on the ice. And when the ice melted, it was sea ice. then the material came to the bottom of the sea, not very deep. Some Danish colleagues gave us these samples and we analyzed them some years ago. So this is one nuclear bomb particle, this one, it's non-detonated particle, so there is no nuclear explosion. It's like raw material. You can see this is the alpha detector. You can see the strips here or this way. So each strip can detect an alpha spectrum. And you can see here number of counts for the strip 6. The horizontal strip, this one here. And this is the vertical strip here. So we can see the location of the particle. So remember that this is 3 millimeter size of each strip. Now, figure D is this one, yeah. I have to read it. It's a singless spectrum means raw alpha spectrum. And the red, or this one, it is 59 kilo-electron volt americium peak gated alpha spectrum. So we selected a narrow gate in the gamma spectrum, for example, from 55 to 65. This narrow area, and generated alpha spectrum from the data shown here. So these are coincidence spectrum. So it can show, you can see here some counts, not very many in this case. Counting time was so small. But these are only americium, nothing else. In normal alpha spectrometry, you see this kind of spectrum. And you have to do spectrum analysis to calculate, for example, how many alphas, how many alphas come from americium, for example. But now we can see it clearly that these are only from americium. In this case, picture E, it's a singless. Singless means it's a raw spectrum. It's a singless alpha spectra. It is this black one here. And I guess that the background, it's this gray one. Sorry, there are no colors in this picture. This is singles, normal gamma spectrum here. This spectrum here. What you can see here is only very, very small peak for americium. When we gate this spectrum by using alpha, we get out this kind of spectrum. See the count rate level. There are almost 100,000 counts per channel here. But there is no background at all, basically. So we can very easily detect what are these peaks. which cannot be identified, not at all here, in the raw spectrum, so-called single spectrum, normal gamma spectrum. From the same spectrum, we look through area from 180 to 190. So we try to look around, are there any uranium-235 signal present? In this case, in the normal spectrum, we cannot see nothing. However, now we can see that there is definitely uranium present in that nuclear bomb particle. Not only plutonium-239. You know that in nuclear bombs there are two main isotopes in fission bombs. Plutonium-239 or maybe 235 uranium. And it's because of the post-processing and putting the time signal to each event. Then, because this PANDA system was very complicated because it is able to locate radioactive particles in the sample. So I suggested my colleagues that could we do it much more simpler way, and we can do it. Let's look at mini PANDA in this case. So mini PANDA system is basically, it's very easy. So you can see the gamma detector here. It's electrically cooled here. This is lead sealed. Now in this case there's lead sealed, and there's an alpha detector here, on which we can put the sample. Thin sample, of course. Because if we are using thick samples for alpha detection, it's not a good idea. So we can use this system for air filter measurements. In this case, there is no position sensitivity. And it operates at ambient air pressure. So these are like normal alpha or gamma spectrometers, but now we put them together and used this list mode technique. Let's look at the detailed picture. So this is lead sealed, this one, gray one. This is electrically cooled gamma detector. This is alpha detector, and we substitute the sample between these two. This alpha detector is so-called CAMBIPS, which can be used in normal air pressure. So what happened here? I didn't do this, but my colleagues did. So a sample was prepared by depositing a droplet of solution containing radium-226 and cesium-134 onto a glass fiber filter. And then a Muller foil, very thin one, was placed above the sample to prevent contamination, especially for the alpha detector. And this is the spectrum recorded by the alpha detector. So you can, when we put radium-226, it was liquid, of course, but it generates, as you know, by decay process, radon, polonium nuclides. All of them are visible there. This is the same spectrum. I will show it once more. So this is linear axis here. Now let's look at the logarithmic axis. So, as you know, alpha particles ionize strongly, so it is possible to detect them efficiently but they are easily absorbed by intervening material. In this case, we have a controlled sample geometry. And alpha spectrometry is, in fact, in many cases, in some of the nuclides, much more sensitive than gamma spectrometry. So this is the same spectrum. I analyzed this spectrum by one of our software analysis softwares. Now you can see the different nuclides present there. So we can analyze also these kind of spectra. Let's see what happens when we are doing coincidences. Again, list mode coincidences. Time signal is collected from both detectors and attached to each quanta. So this is a so-called raw gamma spectrum, normal gamma spectrum. This is gamma spectrum that is gated using alphas. So here we record gammas only when they came same time to the detector when alphas go to the alpha detector. Again, no background, practically no background. So we can easily see low energy peak. So the method efficiently filters away the gamma background. So, sorry about the noise. Why
the lower side is a little bit, peaks are not well resolved?
Yeah, you mean this area?
Yeah.
I think that I don't remember exactly because personally I didn't do this measurement, but I guess that you might know that that because there is radium and cesium emits betas, and also low energy gammas or practically X-rays. So alpha detector can detect also those. And I think this is the reason why there is larger amount of counts. In this case, this is the same spectrum as shown here. This one. So without doing any spectrum analysis like here, this is analyzed spectrum, but if we don't have a good analysis program, so what can be done? We can select from the gamma spectrum this peak, radium peak. You have to note that the peak radium intensity is normally it's very low. It emits only intensity is 3.5%. However, we can in this case detect those alphas when these gammas are detected at the same time and register, in this case, alphas only. So these are definitely radium 226 alphas. Nothing else. So it's this area here, red one. No background here. Okay, now this is quite difficult picture. This is the same sample again. You can see the nuclides and peaks present in this sample, and we identified what kind of peaks are in this spectrum. But now you can see here, this is gamma energy here, and this is alpha energy in the vertical axis. Now these are not spectra, but we put color signal. How many alphas or gammas we detect? For example, as you know, let's look at this example. This is energy, gamma energy is 200 up, 100 up to 900. So as you know, lead 200 at 14 emits these gammas. You analyze these gammas in the lab. So here you can see that you can see the peaks here, 3 peaks, but they are not located here at the energy of 4 or 5 MeV. This, for example, this case shows that there is radon peaks also. So this is very complex way to analyze the spectra. But we will have a lot of information that we cannot obtain from by using only gamma spectrometry or only alpha spectrometry. We can combine these two methods. So another example from mini panda measurement from an individual particle containing americium and plutonium. This is in the low energy part of the spectrum. This is the raw spectrum, blue one. And now this spectrum here is alpha coincident gamma spectrum. We clearly, for example, these very small peaks here, or this one, which cannot be identified from the raw or normal gamma spectrum. And these are the minimum detectable activities for gamma, singless or normal spectrum, and alpha coincident measurements as a function of time. So, sorry. This is time here, and this is minimum detectable activities in terms of becquerels. So in the beginning of the measurement, this coincidence techniques has no big relevance because there are practically no counts in the raw spectrum and also in the coincidence spectrum. But when the time goes on, then there is a difference. What about this Compton suppression device? You know Compton interaction already. So we have one system in our institute. So Compton suppression techniques allows to reduce background from the sample itself. Typically energy is higher than 200 kilo electron volts. So about the name of this Kossu, I have to say you that this is not an animal. This is a name of an alcohol drink. I don't explain this more, but it has some specific details. All right. The idea is this. So we have a germanium detector here, standard detector, surrounded by sodium iodine detectors. And outside there is a lead shield. It's a normal lead shield, nothing else. So why to do this? Sample is located here. Let's see. So, normal detector surrounded by sodium iodine. All right, I explained this already. Let's go to that. Next slide. I already explained this to you, so perhaps we can neglect this one. So you know germanium is a semiconductor, electrons, holes, we can detect the signal. However, in case of scintillators, the light is changed to electrons which are multiplied, and then we get signal out from these sodium iodine detectors. So, quantum continuum. So, it's this area of the spectrum. So, I repeat this because there might be some questions in the examination, I don't know. Let's see. It's an inelastic scattering of gamma photon. As you know, gamma can be scattered and electron moves like this. So only part of the original energy of the incident gamma is transferred to the medium. This is the relevant thing. Part of the original gamma photon energy is lost if the scattered photon escapes the detector. So, and these Compton scattered events cause a continuous spectrum at energies less than the main photon peak. This is the full energy peak. This. The point here is that when there is Compton phenomenon, it can overwhelm weaker real gamma peaks, which might be present here, but we cannot identify small peaks. So, about this Compton suppression system. So, sensitivity can be improved by selecting only good events. In Compton suppression, the signal of the germanium detector is rejected. If there is a signal in these sodium iodine detectors, this is lead shield here. So we reject signal in germanium when we detect signal here. And many of these events are Compton scattered gammas escaping from the germanium detector. And this is, if we filter out the coincident events, the Compton continuum can be reduced by enabling better identification of real peaks. Of course, some nuclides have coincident production of gammas or X-rays, which can cause reaction if they hit the scintillator. But let's see the effect. The effect is this one. So the green one is normal or standard gamma spectrum. And if we react those events if there is a signal in scintillation detectors, then the background is lower. And perhaps we can see signals, weak signals, much more easier. This is the idea for Compton suppression. Not very difficult. So, one more system. We can reduce the cosmic ray background by using this system. So, as you know, cosmic rays are coming to the ground level, and we can detect these signals in gamma ray spectrometry. But in this case, scintillation detectors are outside germanium. And we react the gamma signal if we have signal in one of these scintillation detectors. So this system is also operating in list mode. So this setup is already completed. It's not yet fully tested, so I will not show any pictures on that. So, as I told you before, this was advanced lecture on alpha and gamma spectrometry, and these are advanced things. Sorry, I had to present these, but now I hope that you get or will get some new ideas how to improve your systems. You have already done that. It's great, but let's see what happens in your laboratory. So thank you very, very much listening my presentations. I hope that you understood something. Even though my intonation is totally, English intonation, English speaking is totally different to you. You are speaking so fastly, which means that I have sometimes difficult to understand you, but I'm learning. So, thank you very much.
Thank you, sir. Questions? Compton's suppression system, previous one. Now here, the gammas emitted by the sample,
Yeah.
those gammas will also be detected by both sodium iodide and germanium.
Mm-hmm.
And are detected by both the detectors.
Yes.
And they are also subtracted through.
Yeah. Yeah, that's the way.
Yeah. That means your overall efficiency of the germanium will come down.
That's the case. You can see the spectrum.
Check your values. You do one thing. Target values. What are you? What are very
Calculations.
what we can do now, we within 10% deviation from that.
This is same. Yeah. So we report it as radium 226. You have given it as bismuth 214 and lead 214, correct? Yeah.
Yeah, it's okay. You should get the same thing. 13.
13.
Yeah.
Yeah, that's what I think. 14, 30, 12.7.
So how many of you have got within 20% of this? Raise your hand.
So plus or minus what? Plus or minus within 20. Yeah.
How
within
many of
20.
you have got within 50? Huh?
What are your values? 13.84.
18.
For European.
So it's a 95.
Yes.
So it's 4.4.
12 point.
Where are we? Huh? Raise your hand. Confidently. I am not going to check your. Okay, note down these values and need to leave at 12:45. Yeah. Question number 7.
Yeah.
Yeah.
8 of you moved to HPG, 8 of you moved to LS.
Right. Come. Fast.
ಮತ್ತೆ ನಾನು ಜಲ್ದಿ ಬರ್ದು ಹೋಗ್ಬಿಡ್ತೀನಿ ನಾವೇ ಅಪ್ಡೇಟ್ ಮಾಡಿ ನಾವು ಹಿಂದಿನ ಓಲ್ಡ್ ವರ್ಷನ್ ಅಪ್ಡೇಟ್ ಮಾಡ್ತೀವಿ ಶಿವ ಸರ್
One, two, three, four, five, six. Yeah, please sit. A little bit. Far. No.
Recording.
Sir, I think you can leave. One person, please sit over here. Yes, over here. Yeah. Okay. Three, one can shift. You can shift here. Have shift little bit that side.
Is it okay, sir?
No, it's not okay. You can sit here. And then, six over here. Yeah, please come here. Please. Over here, yeah. This is good. And you can shift. Yeah, you can shift here. Yeah. Sit here. Yeah. Sir can sit. Yeah. This is. But
Part of the
Bharat, fine. Okay. You can shift middle. Yes.
Yeah, I know it. Easy questions, but I can't take
The camera is there.
First is B. This we have to take
Wherever it is required, put it write in one or two lines. Otherwise, just stick here enough.
Yes. Question number 7 is descriptive, and some wherever there is space is left, you have to fill that space. And there is one match the following question.
How much will you
Right?
no for particular for number 7?
Kicking, sir, kicking. No prompting the answer. We'll take your paper and mark 0. Don't make me take your papers. Very simple questions. Leave the on the line top. Select whatever is correct answer. Select the correct answer.
Ready to vote.
Yeah.
Question and person.
Multiple answers can be corrected. Question number 14. Multiple answers can be correct.
All, we distribute the certificate. Okay, then we'll go for lunch.
Kill me.
Five more minutes. Later. Read. Full. Start. Right, we start. We start now. Yeah. Good afternoon, everybody. And we have come to the end of this GIAN program. You had, 6 days of intense lecture program and afternoon practical sessions. And I hope these exercises were, very useful, and you were able to learn the basic as well as some of the advanced aspects of alpha and gamma spectrometry. So we have a formal valedictory function now, in which we'll be distributing the participation certificates to all of you. And for that we have with us Professor Ganesh Sanjeev. He is the local coordinator of the GIAN program, and he is also the professor of Department of Physics, and he is also the head of the Microtron Center, which is in the next, which is adjacent to this carer center. So I invite him on behalf of all of you for this valedictory function. And we have, of course, our expert, Dr. Poi Palanan.
Hello.
Yeah. And we have another professor, Professor Vinay Rajat, who is also now involved in our ongoing research programs of the center. And we have initiated a research program in Kaiga region, which is on dietary survey and assessment of radiation dose. Professor Vinay Rajat is, actively taking up the dietary survey, and I invite him, I welcome him also for this program. And without going into the much details of the other aspects, we would like to distribute the certificate now. So probably one, Avanish or Bharat, you can call the names and distribute. Photo book on book. Okay. I request Dr. Roy Polanan to to hand over the certificates to you. Yeah. You can be here. They will come and collect. Yeah.
Dr. VR, please. Sayantan Mitra. Please come fast. Mr. Padmanabha. Miss Deepika. Mr. Manjunanda.
For the participation.
Mr. Nagaraj. Nagaraj.
Next is what you
Mr. Ian Johnson.
Next is what
Mr. Satish. Dr. Amit.
Thank you for participation.
Mr. Vamsi. Mrs. Sujata.
Thank you for participation.
Dr. Magesh.
Thank you for participation.
Thank you for participation.
Mr. Arun.
Thank you for participation.
Dr. Murugaya.
Thank you for participation.
Mr. Rahul.
For participation.
Dr. Tripti. Mrs. Deepu.
Participation.
Mr. Madan. Miss Sherry.
Now, may I request our distinguished expert, Dr. Roy Polanan, to say a few words about his feelings and also about his You can.
Well, I like to stand.
Yeah.
It is more easier for me. Well, I thank you very, very much for your kindness. It was really a pleasure to keep this course or to have this course for you. I do not feel anymore so much thermal shocks when I first time came here. And also I like much more chili because foods are so spicy.
Yeah.
So I think you are extremely kind for me. I feel like a king or maharaja or something like that. So I thank you very much for participation of this course. So thank you very much.
I now request the local coordinator, Professor Ganesh, to say a few words about this course.
Distinguished speaker, Dr. Roy Polanin, my colleagues, Dr. Karunakar and Dr. Vinay Rajat, and dear delegates, and people who are working here in round the clock for organizing this GIAN program from Kerala. In the beginning itself, I had mentioned that you can exploit his expertise in knowledge to improve your knowledge level, to have a proper collaboration. I'm pretty sure that you got whatever you expected from him, or maybe more than what you have expected from him. And I'm pretty sure that you can trigger whatever untouched parts of the subject by attending this program. And this is the 26th program of our Mangalore University under GIAN program. And this 26th program will be normal education or normal curriculum, or the people who are already working in the field. You have received some kind of input so that you can excel in the field. And the students who are actually the post-graduation students, you can take these 2 credits and you can request the ABC, people who are handling your ABC account to include these 2 credits in your ABC account, so that in case you go for a program, any course after this, if that program is having this particular syllabus, then you can take, you need not attend class, you can take this credit as the credit for that particular program. So you request your concerned education institution where you are planning to pursue your program, you request them to include this credit there. Anyway, all the other required things, we can do it from our end. And I thank all of you for coming over here and being a part of this particular GIAN program. And I also thank Dr. Roy for accepting our invitation from Dr. Karunakara and from Mangalore University, and for being with us for this entire week and enlightening you all with this knowledge and expertise level. And finally, I thank, my colleagues are there, I have to thank them. but it is not necessarily I should thank them, because it is once we take up this job, it is our duty to complete it also. So even then I thank Dr. Karunakara, Dr. Vinay Rajat, and all the people here who have helped you during this particular week for being here safely as well as in a particular comfort level. There could be some kind of discomfort for you. If it is there, please forgive us. We will definitely improve in our next program. I once again thank all of you, and thank Dr. Paulinan for being here and making this GIAN program a successful one. Thank you, one and all.
I thank Professor Ganesh for all this support, because he has been coordinating within the various departments in conducting these GIAN programs. So on behalf of all of you, I would like to thank him also. And of course, now thanks to all the delegates and participants. There might be, as Professor Ganesh has put it, you might have faced some inconvenience, particularly with respect to your stay. Of course, there were some limitations. Whatever best we could do, we have done. But despite that, there could have been some shortfalls, and for that I have to take the responsibility. So, if you feel that this workshop is a success one, and that is because the effort that the entire team has put in, particularly our research team. I don't want to name each and every, you know them more than me also over the weekend. They have been working round the clock to make this research, putting a lot of effort, and they deserve a big round of applause. Finally, I thank one and all, and I wish a very safe and journey back to your workplace. And we conclude this GIAN program now, and we go for lunch. Yeah, we will have a group photo. Yes, one important thing is, of course, you have given the feedback, and over and above, I appreciate that a few of you can come forward and express your feelings about the workshop. Yeah. Express your opinion about the workshop.
It's not mandatory. You can feel comfortable and you can express your opinion.
Yeah.
Sorry.
No, sir, because information I got, the things I could understand was like more. It added to my knowledge, and I'm grateful for that. I'm grateful for the opportunity I got. I understand the things more, and actually, I'm amazed with that. Also to know the labs better.
More.
Very good opportunity to undergo this course. So we have a lot of expectations. Okay. So he initially started with the basics, and then he proceeded to intermediate, and then he proceeded to the advanced levels. Some of the lectures in the last few classes were very amazing, and the spectrums shown. I personally felt that he had taken a lot of efforts in putting each and every slide. So it was very good, and clarify, and even they don't know, they try. Appreciate Dr. Karnakara sir, and thank. I really thank Dr. Karnakara sir.
Thank you. Aishwarya, you want to talk? Yeah. Okay.
First of all, sir suggested me to join this course and get a new dimension for this advanced course. And first of all, we are more delighted to have you,
Thank you.
for your expertized class. It's our privilege to join your class because you are an expertized radiological inspector. And moreover, we could contact with from different regions and different universities. Information about this spectroscopy, and moreover the lab technologies with this structured environment just enriched our information. And thank you for the organizers and the PhD research scholars for for enriching our information in all aspects. Thank you.
Anybody else would like to express your opinion?
Material course instructor and the research support team. I would also thank the clarity that you have provided us here.
Okay.
It was also very good, and interactions also was very good.
It was a pleasure. Yes.
Yeah. Thank you.
Yes.
First of all, I thank to Professor Karnakara sir for inviting for our organization, Yearly Indian Manavala Kunchi. So, first of all, sincere thanks to Karnakara sir. Then, Rai sir, the teaching methodology and the slide is very extraordinary, sir. Because anybody without knowledge of the spectroscopy is starting from basic to at the advanced level. Is explaining the methodology and whatever content. So we are using the spectrophotometry like a sample and energy level, but the result. Behind the spectroscopy, there is a lot of literature is there. Now only I am glad. So I am frankly telling. There is a very sincere thanks to sir. This is the center, sir. The center is the main recommendation, the housekeeping, and some. Or daily up to date things, sir. Again, there's the class is conducted then regular statistical materials are transfer from WhatsApp group. Everything update. Every hospital and whatever things asking to everybody. This sir is telling. Yeah, I'm asking to organization. Come back for the specific for the radar. Then again, Vinay sir. Go for home, then listening the video. Yeah, what's a dedicated? Very most of the all are very strict teachers. And lunch food is very nice. Never forget for your lunch. Then guest house, everything. Then you are our organizations are still in is it? Operation daily side what sir? What sir is I'm behalf of our organization and our friends, sincere thanks to Karnataka sir and again to Rai sir and all Mangalore University and all scholars once again.
Thank you. That's good, yeah.
So it's not a mere hand. Sure, hands-on training and even this was my sincere thanks to our capabilities.
One and all, okay, now we disperse and I wish you a safe journey back.
Thank you.
And let's have lunch together. And we'll have a group photo. Huh? We will not leave this. Acha.